Here is a kitchen argument that has survived Thanksgiving dinners, summer cookouts, and more than a few family group chats. You pull a sheet of aluminum foil from the box. One side is bright and shiny, the other side is flat and dull. And suddenly somebody has an opinion. The shiny side should face the food because it reflects heat. No, the dull side should face the food because it absorbs heat. Or perhaps the shiny side keeps food warm while the dull side helps it cook. People have been flipping foil over casseroles, baked potatoes, leftover pizza, and backyard barbecue for years because the roll appears to be giving us two different surfaces. One looks carefully polished, the other looks unfinished. That makes it seem as though each side must have a different job. But regular aluminum foil is not giving you a secret cooking instruction. The two surfaces were not designed to control your dinner. They are evidence of something that happened inside the factory. And once you understand that manufacturing process, the entire shiny side debate becomes much easier. There is, however, one type of foil where the side really does matter. We will get to that before we finish. Let us settle the useful question immediately. With ordinary aluminum foil and with standard heavy-duty foil, it generally does not matter which side touches the food. You can put the shiny side up, you can put the dull side up. You can wrap a potato without stopping to inspect this under the kitchen light. The food will not meaningfully cook faster because you selected one side instead of the other. The shiny and dull surfaces are not two different grades of aluminum. They are two finishes created on the same sheet because you selected one side instead of the other. The shiny and dull surfaces are not two different grades of aluminum. They are two finishes created on the same sheet at virtually identical rates. But the reason one side becomes shiny is far more interesting than the answer itself. Household foil begins as aluminum that is far too thick and rigid to fit inside a kitchen drawer. Manufacturers pass the metal through large rollers again and again. Each pass squeezes it thinner and stretches it longer. That process continues until the metal becomes the flexible sheet we recognize as foil. The foil becomes so thin and delicate that running a single sheet through the final rollers would make production difficult and increase the risk of breaking it. So the manufacturer places two layers together and rolls them at the same time. Picture two extremely thin sheets stacked face to face. Surface of the top sheet touches a polished steel roller. Those roller-facing surfaces become smooth and shiny. But the two surfaces trapped inside the stack never touch the polished rollers. They press against each other. Those surfaces come out dull. After the final rolling pass, the manufacturer separates the two layers. Each finished sheet now has one shiny side, the side that touched the polished roller, and one dull side, the side that touched the other sheet. The dull side was not treated to absorb heat. The shiny side did not receive a special reflective coating. The difference is simply a fingerprint left by the final rolling process. The myth survives because it sounds reasonable. The shiny side looks like a mirror. The dull side looks rougher and darker. We naturally assume the polished surface must reflect heat while the dull surface must absorb it. And technically, surfaces can differ in how they interact with radiant energy. That principle is real. Reflective foil products are used in building systems called radiant barriers. So the reflective surface faces an open airspace. The airspace is essential to how that system works. A foil-wrapped baked potato is not an attic. When ordinary foil is pressed against food, a baking sheet, or the surface of a casserole, the tiny visual difference between the two finishes is not a useful cooking control. For normal household foil, the difference is too small to produce a meaningful change in how quickly the food cooks. So yes, the shiny surface looks more reflective, but your chicken, vegetables, or leftover slice of pizza will not notice which side you selected. Reflective building insulation requires an air. So yes, the shiny surface looks more reflective, but your chicken, vegetables, or leftover slice of pizza will not notice which side you selected. Reflective building insulation requires an air space to function as intended as a different application from ordinary food wrapping. Here is the rule worth remembering. With regular foil, the two sides tell you how the foil was made, not how it must be used. Shiny means that surface touched a polished roller. Dull means that surface touched the second sheet of foil. That is all. You are not looking at a hot side and a cold side. You are not looking at a cooking side and a storage side. And you are not looking at an inside and an outside. For ordinary foil, either surface may face the food. Now for the exception. Specialty aluminum foils have a non-stick coating applied to one surface. On Reynolds non-stick foil, that specially treated surface is the dull side. The food should therefore face the dull side if you want the non-stick feature to work as intended. But notice the important distinction. The dull side is not naturally non-stick simply because it is dull. It is non-stick because the manufacturer deliberately placed a coating on it. A regular roll of foil does not suddenly become non-stick when you turn the dull side upward. The coating, not appearance, is what changes its function. Specialty products may also include printed instructions identifying the treated side. Read the box rather than relying only on the shine. For regular and heavy-duty foil, either side is fine. For foil labeled non-stick, place the food against the side identified by the manufacturer, commonly the dull side. While people argue over shiny versus dull, often overlook decisions that matter far more, is choosing the wrong material for the job. Foil is useful for covering food, wrapping certain foods, protecting surfaces when the appliance manufactured, and creating sealed cooking packets. But it is not interchangeable with parchment paper, wax paper, plastic wrap, or every type of oven liner. Those materials behave differently around heat. The second mistake, heating element or appliance surface without checking the manual. Foil can reflect or trap heat in places the appliance was not designed to handle. Natural Resources Canada specifically warns that lining certain heating element without checking the manual. Foil can reflect or trap heat in places the appliance was not designed to handle. Natural Resources Canada specifically warns that lining certain cooking appliance surfaces with aluminum foil can reflect heat and damage the element. The third mistake is putting ordinary foil into a microwave simply because the shiny side is hanging away. Turning the foil over does not make metal microwave safe. The U.S. Food and Drug Administration generally against placing metal pans or aluminum foil in a microwave, which may cause uneven cooking or damage the oven. Follow the instructions for your specific appliance, then experimenting. None of these problems can be solved by flipping the sheet over.